Hello everybody, and welcome to the next lecture. So today we're going to be talking about neutron cross-section data. So as discussed previously, neutron interactions usually form a compound nucleus, right? So interactions, when a neutron comes in, it forms a compound nucleus, and then that nucleus decays very quickly into something else. Because of this, binding energy and other quantum effects, cross-sections are much more likely to happen at certain energies, energies that match the the energy that decay will occur at. So, and these energies are called resonances. Additionally, some interactions may have minimum or maximum threshold energy, so you can't have too much energy for a reaction, and you can't have too little. So let's go ahead and start looking at some of the theory and data behind different cross-sections now. So first off, let's talk about elastic scattering cross-sections. I'll say for low neutron energies, elastic scattering is basically billiard ball physics, basically. Right, so a neutron comes in and hits an atom and it bounces off elastically. And so we can say specifically because of this that the scattering cross-section is going to be the cross-sectional area of just the nucleus itself. And so you can say that the microscopic elastic scattering cross-section sigma sub E is equal to 4 pi r squared, where, as you'll recall, we have an expression that we derived earlier in the course about for what the radius of a nucleus is, right? So we can plug that in here, which was about 1.25 times the A number to the third. So this is going to be 1.25 A to the 1/3, and then this squared. And so if we go ahead and resolve that out, we get, and we wanted to do this, oops, sorry, this is 1.25 times 10 to the negative 13 if we were doing this in centimeters. And so then this is, here this is 1.5625 to 5625 times 10 to the negative 26 if we square that. And then this is A to the 2/3 power. Okay? Whoops. Sorry. So, well, I guess I should probably put parentheses around that. So that's a reasonable approximation for what the elastic scattering cross-section is. And if you go ahead and go look up carbon-12's cross-section, for example, and you'll see that sigma E is equal to about 1 barn, which you can go ahead and put together, right? So if you plug that into this expression, you should get something that is pretty close to 1 barn. Okay. So that's elastic scattering. let's move right along to inelastic. So inelastic scattering is where there's an energy loss. So a neutron comes in and it loses some energy when it bounces back off, is actually lost to the nucleus. So a way to think about this is inelastic scattering is when you have neutron absorption and then re-emission very quickly. But that re-emitted neutron is not in the necessarily with the same energy, or it's not with the same energy. The energy of the system, some of that energy goes into exciting the nucleus itself. So so it comes from the neutron's kinetic energy, and therefore because of this it doesn't exist below some threshold. So I'll say this reaction does not exist below some threshold energy, okay? Which represents the first excited state of the nucleus, right? You have to be able, the neutron has to have enough incoming energy to at least get the nucleus to the first excited state, I should say, of the compound nucleus, if not even higher, okay? Should also note that this threshold energy decreases for increasing a number because it's easier to get to the first excited state for larger nuclei. Right, so again, look up, you can look up carbon-12 and U-238, and you'll get, you'll see that the inelastic scattering cross-section is different. Oops. Or it should be, the threshold energy is lower for the U-238 than it is for the carbon-12. So sigma sub I. Okay. All right. Okay. So the next kind of, so that's all we'll say about inelastic scattering. Ooh, not inel. Wow. I misspelled these. Elastic. It's probably what you thought I was going to change. Not in a salt stick. It's pretty funny. Oops. Okay, so the next kind of reaction is radiative capture. So recall that this is when a nucleus absorbs a neutron and emits a gamma particle, or a photon, so we call that sigma sub gamma. And we'll say that, so for most nuclides, it's easier to capture a neutron the slower it's going, right? So because there's more interaction time, it's not, the neutron's not zipping by really quickly, it's going more slowly, and so it's easier for the neutron to be absorbed into the nucleus. And so for most nuclides, it is easier to capture a neutron the slower it is going. Thus, what we have, this is an expression in terms of velocity, right? So sigma, or specifically inverse of velocity. So sigma is, I think that's the thing, proportional to 1 over the velocity. Oops, I think maybe prop 2? There we go. Forgetting my LaTeX commands. And velocity we know is proportional to, or energy we know is proportional to the square of velocity. So this is in fact also, the sigma gamma is proportional to 1 over the square root of energy. Square root of energy. Oops. Even though I knew the command, I mistyped it. Okay. And this is obviously because kinetic energy, since we're dealing with kinetic energy, this is E equals 1/2 m, the mass of the neutron in particular, v squared, which, oops, 1/2 mv squared, which thus implies that v is equal to the square root of 2 over the mass of the neutron times the energy, right? So sigma gamma is actually proportional to this 1 over this term. Okay. Okay, so did I do that right? Oh, nope, sorry. This is wrong. This is 2, sorry, the units of that would never work out. Sorry, 2e. Mess that up. 2e over m, mass of the neutron squared. So, and for examples of this, you can look at uranium-238 and silver, or yes, gold 197. However, this model fails for what we called resonances before, which is when it's more, when certain energies are much more likely to be captured. And so resonances themselves can be described as Gaussians, error functions, or Green's functions. And so in particular, we'll call the Brett Wigner one level formula is used to describe resonances. And so this is where the radiative capture cross-section is equal to, or as a function of energy, is equal to gamma, which is the wavelength of the neutrons here. So sorry to reuse this term here. Gamma squared times g, which is what's known as a statistical factor, 4 times pi, and this is times another fraction which uses gamma functions, or so uppercase gamma, which is gamma sub n, which is the neutron width, times gamma sub g, which is the radiation width, is what it's known as, divided by E minus, or the energy that we're coming in at times the resonance energy, or minus the resonance energy, squared plus the radius of the neutron. Oh, sorry, no, plus, not the radius, plus uppercase gamma sub n plus gamma sub g. That term squared divided by 4. Let's see if I got that right. Yeah, that looks right. So, no, that's a lot, but in all of this, what we'll see is that, go ahead and define these. So gamma sub r is the wavelength of neutrons, so that it, with energy ER, and so that is, or with the resonance energy, so this has, because it's a wavelength, it's got units of 1/centimeters, and then E sub r is the resonance energy in MeV. G itself is this scaling factor called the, or it's a constant, which is called the statistical factor. And as we said before, there's a couple other pseudo constants for any particular resonance. So gamma sub n is the neutron width and measured in units of energy, and gamma sub g is the radiation width. Also in units of energy. Okay? So radiative capture has, so if we wanted to put these two pieces together, what we would see is we would see if we were plotting, oops, let me draw axes for us. So if this is energy on this axis, and this is sigma, the sub gamma, the cross section, what you'd see is that for low energy neutrons, this is on a log-log plot, it's much more likely that we'd capture lower energy neutrons than higher energy ones. And then occasionally, what we'll see are these, oops, let me, Gaussian kind of resonances where for some energy width, or maybe for a couple of them, oops, that one was actually pretty good. You know, that will have, it'll be much more likely to capture a neutron for a small energy domain, right where basically the neutron or the nucleus has a neutron-sized hole for that particular energy. Okay, and it'll just go ahead and be captured. All right. Okay, so that is the radio capture bit. Moving on. we have charged particle reactions. So these are ones, these are cross-sections such as, you know, proton reactions, or reactions that emit protons, reactions that emit alpha particles, right, etc. Okay? Oops. Don't need that. So, these sorts of cross-sections are often small. However, they typically have a 1/v dependence to what we call, right? So the slower the particle's going, or the slower the incoming neutron is going, the more likely it is to interact. And they also have a threshold energy. So both, they're more likely at lower energies, but you have to have a certain amount of energy for it to occur in the first place. Is the way to think about that. Okay, and then the total cross-section, which we've called sigma sub t. This is, so for low energy neutrons, right, we've defined our total cross-section as the sum of the scattering cross-section and the absorption cross-section. So if we don't have inelastic scattering, and we're just looking at radiative capture for the moment, right, so we're below the threshold for inelastic scattering and some of these charged particle reactions, we can say that sigma t is equal to 4, right? This is equal to sigma sub e because we don't have inelastic scattering. So it's just the elastic scattering. And sigma sub gamma because we don't have these other types of reactions that produce other kinds of charged particles. Okay? And so if we wanted to expand that out, what we would see is that sigma sub t, based on our definitions above, is equal to 4 pi times the radius of the nuclide, or the nucleus, squared, like we saw above. Up here, right, we could do this based on a number if we wanted, plus some constant c divided by the square root of the energy. That's pretty cool. So for some constant c. Now which one of these two terms here dominates really depends on the energy and the constant c, right? So some are going to be more likely to absorb neutrons, and some are going to be more likely to just have them elastically scatter off, bouncing away into the future. Okay. All right, so that's kind of a brief overview on the history, on the theory here, on how these things work. So let's take a slightly deeper dive and talk about scattering in particular and energy. and energy loss. Okay. So here we will determine the energy of a neutron after a collision via the conservation of energy and momentum. So determine the energy of a neutron, of a neutron after a collision via our favorite rules, conservation of energy and momentum. So, as you'll recall, right, so what we have in this picture is, or if we wanted to draw a diagram of what was going on, we have some nuclide in the reference frame of the nuclide, and then we've got a neutron coming in to hit it. Okay, and so this, so we'll call this N, and okay, so let me put this. So initially, right, we've got this nuclide has some energy and some momentum vector, and then this, or the neutron has some energy and some momentum, and then this energy of the nuclide E sub n and the momentum of the nuclide P sub n initially are both equal to 0. Okay? And then after this reaction, what happens is that the neutron goes flying off with some angle theta and some E prime and P prime. So this is the pre-version, and then here on the post, we have the nuclide go flying. The nuclide itself goes flying off with some other angle phi. Oops. No. Okay. And so so this has some E prime, P prime, and then let me move this around. Yep. And then this has some En prime, Pn prime. Okay. Okay. So from our conservation laws, we know a couple of different things. So first off, we know that E, from conservation of energy, we know that the energy of the neutron plus the zero energy of the nuclide is equal to the value afterwards, which is E prime plus the energy of the nuclide prime. And we know, remembering that we are in vector notation, we know that our momentum initially is equal to the momentum of the nuclide afterwards plus the momentum of the neutron afterwards and the momentum of the nuclide afterwards. So vector of P sub n prime. Right. Okay. So those are our conservation laws, and one of the annoying things here is that we have both these angle theta and phi, and so we want to kind of eliminate those. So I'm just going to remind you of the law of cosines. So if we've got, so say that we have a triangle. Let me go ahead and draw this. So if we have a triangle, for any triangle that we have, if we call this side, so we'll use lowercase letters to denote sides, and so and then uppercase letters to denote the angles. So if we have A, and the angles are opposite their side. Oops. Okay. So for this situation, for all rotations of this triangle, what we have, the law of cosines states that the length of c squared, so c squared, little c squared, so that side length, is equal to a squared plus b squared minus 2ac, or sorry, 2ab times the cosine of the angle C, big C. Okay. And so you could mix and match any of these, but as angles, but as long as this holds, this is a true statement. And so we can apply this to our momentum equation. So if we go back and we look at our this expression, what we can do is we can bring in this momentum here, the side length of the momentum here. That will form the bottom of the triangle. Bring this momentum up, that forms this one side, and so what we get is we could relabel this as, because this would be like, could form a triangle with P, oops. So this one comes down here. So this would be P, and then this one up here is the same, so that is P prime. And then this piece moves up, and so this nuclide piece moves up, and so that forms this side length, and we get P sub n prime. Okay, so now we have a nice little triangle here, and the thing that we don't know is the angles, but this this angle here is identically theta. So this is theta, and so now we know we don't need to have P prime rather in terms of our angle phi, right? So this is phi over here, but now we don't need that because we can put it in terms of cosine using the law of cosine. So applying this, basically what we'll get is we can use this to say P prime squared is equal to p squared plus, p p sub n prime squared is so the momentum of the nuclide squared is equal to the momentum of the neutron squared initially, plus the momentum of the neutron squared after excuse me, after the collision, minus 2 times p the momentum prime, momentum afterwards, times the cosine of theta in this case. Oops. Something is not happy with me. Prime. It's probably this. There we go. Okay. Right, so now we have eliminated phi, which is the important bit. And so, right, so from mechanics, so that's one variable down. Okay, oops. So we have eliminated phi, and from mechanics, we know that P equals the momentum equals the mass times the velocity, and thus the momentum squared equals the mass squared times the velocity squared. And we also know from previously in this lecture that, and mechanics, that the velocity squared is equal to 2 times the energy divided by the mass. Right? So putting those pieces all together, we can say that p squared, or the momentum squared, equals the mass squared times the velocity squared, which is the 2e divided by the mass, which thus the mass, one of the masses cancels, and so you get 2 times the mass times the energy. So that's what the momentum squared is. Okay. So if we put this, if we plug all this in, right, so the mass of the, so we have our mass of our nuclide, or our, sorry, not our, so let's say that our mass of our nuclide, we'll call our nuclide A, capital A, and we'll call the mass of the neutron N. So, so changing variables a bit here, we'll say that the mass, we can plug all of our expressions in here. So there's a 2 in every piece, right? And so then we'll have the, let's just go ahead and do it, I guess. So 2 times the mass of our nuclide A times the energy of A prime is equal to 2 times oops, not 2 prime, 2 times the mass of a neutron times the energy of the incident neutron plus 2 times the mass of the neutron times the energy of the exiting neutron, E, minus 2 times the square root of this expression times the square root, right, because that's momentum squared, and now we need momentum. Times cosine of theta. Okay. Oops. Okay, so instantly you can see that there's a 2 in every one of these expressions, so we can go ahead and cancel that out. So if we do this, and there's a 2 in this square root, in both of these square roots, so these two. So let's just get rid of, let's start with this. So this 2 cancels with those. This 2 cancels, but then there's a 2 in both of these square roots, so you can, square root of 2 squared is just 2. And so that comes back out. Okay. So that's good news. And we can make the approximation, right? So it's not, right, we know that an atomic mass unit isn't exactly equal to the mass, or to 1 unit of mass, but it's close to true for these calculations, right? It's about 1 part per thousandth off. So we can say that the mass of A divided by the mass of N is approximately equal to the A number of the system. Okay? And so if we divide by the mass of this whole expression by the mass of the neutron on both sides, right? There's a neutron mass in all of those terms. We can thus go on to approximate this as just the mass of the A number times the energy of A afterwards divided by square root of E prime. 2 times the square root of E prime. Okay? And so this is great. So what we're looking for is, what we want to do is we have an equation here with both E prime, which we want to find, and E prime sub A unknown. And we know from up here that E prime, from our conservation of energy, that E sub A prime, right, the energy of the nuclide after the collision is equal to the energy of the neutron before the collision minus the energy of the neutron after the collision, right? So the neutron gives some of its energy to the nuclide A, and that amount is just the difference between them. And so we can go ahead and substitute this into our expression above here, and then we'll have an equation with only one equation with one unknown. So this is then going to be E minus E prime, and yeah, there we have it. So now all we need to do is solve for E prime. So another way of thinking about this is, well, first let's rearrange, okay? So to get this in powers of E prime. So one way to rearrange this, let's subtract this from both sides, the left-hand side from both sides. And what we'll see, so we want to get a 0 over here. So we'll say that 0 equals, if we do this, we have minus e prime here, a times e prime plus this e prime, so this is a plus 1 times e prime. And then, and then we've got this e prime in a square root, so we could write this as 2 square root e times cosine of theta times the square root of e prime, right? And then minus the remaining, this has a minus here. Minus the remaining terms, which are a minus, or 1, so this is a plus e, and then this would be a minus a times e, so this is minus a minus 1 e. Okay? So what do we get by this expression? Well, what's nice about this is that this is actually a quadratic equation in units, or not in units, with respect to the square root of e prime. And so if we apply the quadratic equation, we can solve this for the square root of e prime. So doing the normal b plus or minus the square root of b squared minus 4ac divided by 2a, with this is a, this is our b in our quadratic equation, and this is our c. We can see that sneezy today. The square root of e, e prime, square root of e prime is equal to the right, so this is, sorry, let me type all this stuff in. So this is fraction, so 2ac that on the bottom, that's going to be 2 times, or 2a, sorry. So this is a plus 1. That's on our denominator. And then on our numerator, we have negative b, which is already minus 2 times the square root of e times cosine of theta plus or minus the square root of b squared, which is going to be 4 times e times cosine squared of theta minus 4ac, which is minus 4 times a plus 1 times a times E times A minus 1 times minus 1. Is that right? Oh, yeah. Right, because that is a minus. There's a minus sign there, right? For A. Yes, I think that is correct. Is there an E there? Yeah, okay. For E squared, A plus 1. Oh, yeah, that's right, because there's an E. Okay. Yep, that's right. So, if you go ahead and work through this algebraically, and then square the whole thing, which I won't put you through right now, you can get this down into the simplest form, which would be E prime equals, so the exiting energy of the neutron is equal to E, the incident energy of the neutron, divided by the atomic mass plus 1 squared times the square root of, oh, no, sorry, this isn't the square root yet. This is this is the cosine of theta plus the square root of a squared minus sine squared of theta, and all of that squared. Okay, so this is the simplest expression that we can obtain. Now there's a couple of interesting limiting cases for this. There's a case where theta equals 0. That's good to look at. A case where theta equals pi over 2, and the case where theta equals pi. So theta equals 0 is this glancing blow. The neutron just goes directly past it. Theta equals pi over 2 is where the neutron comes in and it bounces orthogonally off. And theta equals pi is when the neutron comes in and then bounces directly back the way it came. And so those are all interesting and important, and you should plug in those numbers to this equation and see what you get. But I think that's about all the time that we have for today, so thanks a lot, and I'll see you next time.